Welcome to The Explainer. Today we're going to pull back the curtain on chemical reactions and find out about the secret story that's happening just beneath the surface. So you see a balanced chemical equation. It seems pretty straightforward, right? You've got your reactants on one side, products on the other. Easy. But what if I told you that simple line of text is actually hiding most of the action? Yep, that's right. Think of the balanced equation as just the final scene of a movie. It shows you who was there at the start and how things ended up, but it tells you absolutely nothing about the plot, the twists, the drama, the good stuff that happens in between. So to really get what's going on, we have to uncover that hidden plot. We need to figure out the actual step-by-step process that takes us from point A, the reactants, to point B, the products. And that secret story, it has a name. It's called the reaction mechanism. It's the precise step-by-step sequence of events. It's not just the what, it's the how. You could even think of it as the secret choreography of the molecules. All right, let's stop talking in analogies and dive into a real classic example, the decomposition of ozone. This is going to show us exactly how we can deconstruct a reaction into its core parts. Okay, so look at this. The big picture, the overall equation, says 2 ozone molecules just magically turn into 3 oxygen molecules. But the mechanism, the real story, it reveals that's not what happens at all. It's not 2 ozone molecules just bumping into each other. Instead, look at step 1. One ozone molecule actually breaks apart first. Then, in step 2, that little lonely oxygen atom goes and collides with a second ozone molecule. See? It's a whole 2-part drama. Each of these individual steps has a name. We call it an elementary reaction. Sticking with our movie analogy, these are the individual scenes. And here's the really cool part, the big secret. For these single steps, and only for these steps, you can figure out the rate law just by looking at the equation. That's a huge shortcut. Hey, did you happen to notice that single oxygen atom? Look back at the steps. It gets produced in step 1, and then, boom, it's immediately consumed in step 2. It's not in the final equation at all. We have a special name for that. It's called an intermediate. It's kind of like a crucial supporting actor who's essential to the plot, but, doesn't make it to the final credit. Okay, so now we can start classifying these elementary steps using a concept called molecularity. Now that sounds like a big, fancy word, but don't worry. It's really just a simple way of asking how many molecules are actually colliding in this specific step. It's pretty simple. If just one molecule is doing its own thing, rearranging or breaking apart, like that first ozone step, we call it unimolecular. Uni for one. If 2 molecules have to smash into each other, we call it bimolecular. Bi for 2. And this is that powerful shortcut I was talking about. For these elementary steps, the molecularity, literally just counting the molecules involved, tells you the rate law for that step. It's amazing. So you're probably thinking, okay, what about 3 molecules? Well, you can have that. It's called termolecular. But, and this is a big but, they're super, super rare. I mean, think about it. Getting 2 things to hit just right is already tricky. The odds of 3 separate molecules all colliding at the exact same instant with a perfect angle and enough energy, it's just astronomically low. So you almost never see them. Okay, this is where it gets really interesting. We have these different steps, right? Some of them are probably fast and some are slow. So how do all those different speeds combine to give us the one single overall speed for the whole reaction? Well, think about an assembly line in a factory. You could have a bunch of super fast workers, but if there's one person on the line who's really, really slow, the entire factory's output is limited by that one person, right? They create a bottleneck. And guess what? Chemical reactions work the exact same way. That bottleneck step, the single slowest step in the whole mechanism, has a very important name, the rate-determining step. It's the one that governs the overall speed of everything. It sets the pace. So if you're a chemist and you want to speed up the whole reaction, you don't focus on the fast steps. You have to find a way to speed up that one slow step. And this is the crucial point. We can use this whole idea of a rate-determining step to actually solve real chemical mysteries. So let's put on our detective hats and investigate the reaction between nitrogen dioxide and carbon monoxide. All right, here's the case file. Chemists ran the experiments and found something really weird. Check this out. Above 225 degrees Celsius, the reaction speed depends on both of the reactants. Makes sense.
But below 225 degrees, the speed only depends on the nitrogen dioxide and it's squared. What? How can the same exact reaction have two totally different rate laws? There's only one explanation. The secret story, the mechanism, must be changing with temperature.
Okay, let's look at our first suspect, the high temp reaction. At those high temperatures, the molecules are buzzing with energy. They have enough juice for a simple, direct, one-step collision. It's a bimolecular elementary reaction. And if we predict the rate law from that single step, it's a perfect match for what the experiments show. So case closed for high temps. That's our mechanism. But what about at lower temperatures? The molecules are a bit lazier, so a different, easier path is favored. Here, our theory is a two-step mechanism. And the key, the absolute critical piece of information, is that the first step, where two nitrogen dioxide molecules have to find each other, is the slow one. That's our bottleneck. The second step happens in a flash. So remember our assembly line? The whole process can only go as fast as its slowest step. That means the rate for the entire reaction is set by the rate of just step 1. And what's happening in step 1? It's just two NO2 molecules colliding. And since that slow step is an elementary reaction involving two NO2 molecules, its rate law is rate equals K times the concentration of NO2 squared, which is, drumroll please, exactly what the experiments told us for low temperatures. See? The mechanism explains it perfectly. It's an awesome example of how these hidden stories let us make sense of data that seems totally confusing at first. Case closed. Okay, so let's zoom out for a second. Why does all this matter? Why do chemists spend so much time and energy trying to figure out these secret molecular stories? Well, because understanding the mechanism is pretty much everything. It's what takes us beyond a simple before and after picture to the actual detailed journey the molecules take. It explains why things like temperature can completely change how our reaction behaves. It lets us test our ideas against what really happens. And maybe most importantly, the mechanism is the bridge that connects the theories we write on paper to the real results we see in the lab. It makes it all make sense. So, the next time you see something that looks simple, I want you to remember the reaction mechanism. What looks like just a single, straightforward event is almost always a hidden story, a complex sequence of steps happening under the surface. It makes you wonder, right? What other simple things in your world have a secret, complex story just waiting to be discovered?